Yeah.
Want to have someone speak and see how it sounds in the room?
Oh, my name's Art.
Art.
She's muted.
Hi, Martin. Thank you for joining us.
Try again. The online audience, can you hear us? I think that means yes. No.
Do you hear me?
Yes. Yes, can you hear us?
Yes.
Okay, you're good.
I can hear people, but some are very muffled and some are somewhat clear.
If I speak through the microphone, can you hear me more?
I can hear you more.
Okay, so to drown out, so we have ceiling mics to pick up everybody's conversation. So the speaker will have to speak through this phone to kind of drown out that conversation.
You have his little hand.
Give me a sec.
I'll show you what I'm gonna say and then you can decide where you want to be. Yes, it's, I think it's
Testing.
recording.
Testing.
Can you just gonna say this?
If I turn on the lavalier, the audience. Okay, you want me to read?
Hi, Martin and Gretchen. Is this a good volume for you? Online?
Yes.
Okay.
It could be picking up there, so.
Oh, just find out if it's one more time. Yeah. Is it still a good volume? Can you hear me? good?
Yes.
We good to go?
Okay.
The volume seems good. I only hear clear voices every so often.
Do we?
I can hear Gretchen very well.
Thank you, Becky.
Oh, I'm sorry.
Hi, everyone. So thank you for joining the keynote speaker panel discussion. We will have some folks online and 2 of our panelists are online and 2 are here. David, hi, come on up. And you're up.
Where do you want me?
Either side. Whichever you want to sit.
You have to point the camera.
We'll point the camera, yeah.
I moved it.
It's just 2 of us all.
Is this? Yes, please.
Easy for everyone.
So my friend Becky here will be facilitating our discussion. And I just want everyone here to, first, big reminder, the mics in this entire room are live. So the folks in the webinar can hear your side conversations. If you need to take a phone call or have a conversation, you can welcome to get up, head back where the snacks and foods are and have a conversation back there. But just keep in mind, we will be able to hear you if you do it in this room. And then the other thing I just want to mention for everyone in the audience and here in person, online and in person, that we today, all of our activities are really meant to get your mind thinking, to sort of spark ideas and creativity. So as we have this conversation with our panelists, just keep that in mind that we're thinking we're trying to think of new ideas and new opportunities for collaboration and new approaches to the different topics we're talking about. So with that, I'm going to hand this over to my great friend Becky.
All right. Well, we are here today because today's grand challenges will not be solved by one discipline. NEREID has chosen to focus our efforts on fostering convergence within our membership. And so using the NSF's definition of convergence, we want to encourage projects and research that are driven by specific and compelling problems and that show deep integration across the disciplines. So we brought together these specific 4 people on our panel because all of them are involved in projects and research that build bridges across fields. So today we have David Grinspoon in the room. We have Martin Ogle online. We have Gretchen Stallman online. And we have Nirav Merchant in the room. And so what I'll do is pretty much informally be asking you questions, and anyone can offer a thought. You can all offer a thought on the questions. If nobody offers a thought, we'll move on to the next question. I'm going to start. Hand this over to you guys. Whoever wants to grab the mic at the time. You're sharing. So first, we just want to get an introduction to the panelists. And if all of you could give us a brief introduction to your work and a little bit of background, very briefly, because we want to move into the meat, and especially what brought you to your field. Why did you choose what you're doing?
Okay, I'm David Grinspoon. I'm a planetary scientist, astrobiologist. Sometimes I call myself one, sometimes I call myself the other. I'll explain the background of that a little bit. So when, well, very briefly, when we started sending spacecraft to the other planets, there was no such field as planetary science. There was a need for scientists who could interpret the data coming back from other planets. And astronomers weren't the right people. They looked at little dots of light and telescopes. Earth scientists had a lot of the tools to do it, but they were used to thinking about Earth. So a hybrid field formed called planetary science, which was really Earth scientists taking on new problems and working with astronomers and space engineers and so forth. And I, as a child of Apollo and enthralled by the early space missions that were happening when I was a teenager in the 1970s, you know, the first landing on Mars and all these exciting things. I was very captivated and wanted to go into that field. When I was an undergraduate at Brown University in the late 1970s, there was no major in planetary science. But at Brown University, you're allowed to make up your own major if you get approval of a faculty member to sponsor you. And I think I might be the first person with an undergraduate degree in planetary science, at least that I know of, because that's what I called it. And I got my degree in that field. And then when I went to grad school at University of Arizona in a department that was called planetary sciences, none of my professors had degrees in planetary science because they were the first generation. So they had degrees in geology or physics or atmospheric science or chemistry. Now that same department, a generation later, all the professors there have their PhD in planetary science. So it's sort of I've seen people in our field have seen the evolution of a new field of really a convergence from separate disciplines because of the need to solve this problem of how do we treat the planets as planets, And then something more recently, astrobiology came into its own really in the late 1990s. There was the fringe exobiology where it wasn't really respectable to think about alien life. And then we made a number of discoveries that made it seem more probable that, hey, maybe we could find something. And I won't go into detail about what those discoveries were, but NASA sort of embraced astrobiology. And that was kind of the same process of bringing together fields. But in this case, biology came in and they had to work with astronomers, as in, the title, and planetary scientists and earth scientists. So it was a new kind of synthetic field. And and I, having, sort of recently got my PhD, was sort of primed to like, hey, I'm an astrobiologist now because we can be astrobiologists. And so people, it's same thing though, people came from other fields. Nobody was trained by astrobiologists because there weren't any. And I remember very clearly the first few national astrobiology conferences were really frustrating because people did not speak a common language. So there'd be a talk by a chemist saying something really interesting, but only the chemists in the audience would understand it. And the astronomers or biologists would be outside the room going, did you understand any of that? No, did you? And then same thing when there was a talk by an astronomer. And out of that though, to their credit, the NASA Astrobiology Institute realized that was a problem and instituted a lot of sort of continuing education and trainings, and made part of their meetings where people from different fields would educate people from other fields. And I think it's worked. I think there's kind of a common language now. And a lot of the scientists have learned to speak each other's languages, and sort of now astrobiology is a field where people maybe come from a specific subdiscipline, but know enough so they can talk biology and talk astronomy. So it's been kind of, I think, a successful evolution of convergence between fields, and it's spilled over into education in a very positive way, because I think a lot of the people, especially the young people coming in up in that field, are very good science educators because they've had to immerse themselves in this sort of broad set of perspectives. So what I do more specifically is climate modeling of other planets mostly, although a little bit of Earth, using the techniques of Earth climate modeling. And I'll stop here, but the one thing I will mention is that that I think has equipped me and some of my colleagues to have a different kind of effectiveness in some of the societal climate conversations, because you can come at it from a slightly different perspective. People tend to have these entrenched views. And I even had one experience with a climate denying congressperson who I learned was also a big fan of planetary exploration, where I went into his office and the conversation, I wasn't like, hey, let's talk about climate. I was like, let's talk about Venus. And in a roundabout way, ended up talking about global warming and some of the need for more research. And so I've experienced that coming at things from a slightly different disciplinary direction can be a powerful way to kind of break through mental blocks in the education domain as well.
Can we hear from somebody on the line about that same question of a little bit of your background and what brought you to your field? I see Gretchen.
Oh, okay, I can go. So my field is library and information science. How I got to this field, this really started when I was working at the circulation desk of an academic library back in the early 2000s, late 90s, early 2000s. And that was like a really interesting time for libraries in terms of technology and information, knowledge going online and being more accessible. So that got me interested in the field of library and information science. At the same time, I happened to learn about a job at the National Radio Astronomy Observatory. And so I got a job there in 2007 and completed my master's degree in library and information science while I was working at NRAO as a documentation specialist and technical writer. So I was managing engineering documentation for a large telescope project that is managed by AUI, actually. I'm sure most of you have heard of ALMA, or the Atacama Large Millimeter Submillimeter Array project. So that led to an exciting opportunity for me to live and work in Chile from 2011 to 2013. And then I decided to also go to the University of Arizona for my PhD. This experience of working with a large scale telescope project, it really got me thinking about the not only the technical and information dynamics with implementing such a project, but also the social and political aspects of doing big science. So I went to the University of Arizona School of Information to kind of explore these issues related to collaboration and technology, especially in terms of data, how we create data, how we share and manage data. I had some interesting graduate assistantships there that kind of led me to my current interests. One thing that I did do, and I actually got to know NEREID there. I worked with my advisor, writing grant proposals and working on a project called Astrolabe, which was an NSF-funded initiative to build tools for astronomers in a cloud-based cyber infrastructure environment that probably NEREID will talk about a little bit later. So then I was working with astronomers and also having this background working for ALMA. I've kind of continued my career as a librarian, as an information specialist, but with a particular interest in astronomy, information, and data. So at the end of all of that, I ended up on an academic career path. I finished my PhD in 2020. I've been a faculty member at Rutgers University for the past few years, and this fall I will transition to the School of Information at Florida State University. Just to briefly, I'll probably get a chance to talk more about it, but my research interests are in a few buzzwords, long-term management of research data, scholarly communication, and infrastructures for data curation. So, broadly speaking, I'm interested in social, institutional, and technical influences on the decisions researchers make about sharing and seeking data and findings, how those influences and decisions vary across disciplines and infrastructures, which is why I'm here today, and what resources and services we could develop for more open, reliable, replicable science. And I'll just conclude with mentioning that the courses I've taught in the Master of Information program and the undergraduate information technology and informatics program include human information behavior, organizing information, digital curation, digital libraries, and social informatics. So hopefully that gives you an idea of my background and why I'm interested in these topics.
Gretchen, NEREID, can we hear from you?
Sure. I'm really glad to hear that there are 3 wildcats on this panel. I don't know how this was by design or. Yeah, I'm also a product of University of Arizona. So I started as a systems engineer, and I was spending time programming robots to build parts where there were multiple machines that could do different things. And if you wanted to make something, it had to go to the first machine to get made into a circle, a next machine to make a hole. And all of these things were complicated, but you could make that happen. And finally, one day I told my advisor that biologists are going to need this. Manufacturing has this covered. Everybody's doing this. Why are we wasting time? In a crowded field, we should be building this for biologists. And he looked at me and said, focus on what we need to get done. And at that point, what I was doing was also using a networking protocol called GOSSIP, which is Government Open Systems. None of you would have heard of it. Google it. I'm sure you might find something. And I told my advisor, there's this whole thing called World Wide Web. This is 1992, 93. That is being born. These machines should be talking to each other using TCP/IP and the web. And literally, the paper that we wrote was rejected by every journal. Every journal, 1990. It finally got published in 1996. So my graduation was kind of challenging when journals said, what are you talking of? None of this is real. So it was kind of fun to go through that phase of my life. And I worked with biologists, and I'm thankful to my advisor to taking that risk, because my funding as an RA was from neuroscience. And so I was working with folks that had no idea what I did, but they wanted the skills of optimization. They wanted to work with me on connecting systems. And that made me so happy, because they were very grateful for everything I did. While on the manufacturing side, they're like, phew, we have a bigger robot in Germany, or that thing does better there. This was a completely, start up a new field, like what he said. So there was a lot of encouragement on anything new. So I'm grateful to my colleagues in the neuroscience. Fast forward a few years, and then I started building systems that would allow people to manage large amounts of data, large amounts of computation. And that was the birth of one of the projects that Gretchen is talking about, which is now 15 years old, and is still running. And it has about 120,000 users all over the world. It has petabytes and petabytes of data, and it does many things for many individuals. We were born funded by NSF to work on grand challenges in plant sciences. This is 15 years ago. And we spent 2 years talking to the community, and the grand challenges were not as grand as what NSF wanted. People were struggling with connecting what was large-scale computing that NSF was funding, and the biologists weren't able to use it. And there was a little digital divide. And the groups that knew how to use it were already well-funded. So are we just allowing the well-funded groups to get more well-funded? Or are we going to democratize what NSF is trying to do? And so they literally had to change the focus of our project based on what we learned. And we said, if FedEx and UPS is part of your data management, you're not going to be able to scale your science. And so fast forward that, we created a lot of cloud capabilities and allowed different disciplines. And today, if you go and get the black hole image, many of you would have seen it, the DOI resolves into cybers. So a massive project like that, and our involvement was very nominal, because this is like Lego blocks. We allow the community to put whatever they want together to solve their problems. Much like Lego blocks, we made sure some of them fit, but it's your vision of what you want to make with those Lego blocks that allows you to do that. And given the number of educators in this room, I want to specifically point out that when we designed Cybers, we made sure that the educators that were especially coming from undergraduate, high schools, PUIs, all sorts of institutions that were not R1s, they all had the same access to the same technology, the same size of data. And if you wanted to teach a tutorial with real scale data, we were allowing you to do it. And if you had to start with the toy example and 2 of your students wanted to venture into something that was more complicated, all of that was available. So I felt really good about how educators are given access to the same exact infrastructure. And I can keep talking more about it, but I'll return the mic back to you.
Keep it there, because I think my questions. Do we have Martin? It seems like we're having a little technical. Do we have Martin with us? Yeah, it looks like. Let's move on, and we will, when we back in. Yes. Martin, let us know if you can hear us and if you're ready. We will circle back to Martin. Next question. We're thinking about convergence. What are, or maybe what could be, the impacts of convergence across Earth and space science? For example, if we use exoplanet data to inform climate models and vice versa, but for you, what do you think the impacts are of convergence?
Well, I think the impacts of are profound between Earth and space science on a couple of different levels. I mean, in my own subfield, I mentioned I do climate modeling, and there are many examples of very practical things that we have learned from studying other planets that have fed back on.
Do me a favor. What? Just get off. Are you on the internet? Could you just get?
There are several examples of concrete examples of things we've learned from studying the climates of other planets that have made us better at understanding various environmental issues on Earth. And just not to go into detail, but to sort of list a few, the same people that in the 1970s started working on global dust storms on Mars. You know, how does it affect the climate of a planet when the atmosphere fills with particulate matter? Were the same scientists using the same models who figured out what happened when the asteroid hit Earth 65 million years ago and caused a global dust cloud, which led to a mass extinction, largely because of the climate impact. And then they were the same scientists using the same models who came up with the theory of nuclear winter, because the same problem in a slightly different guise. What happens if the stratosphere of an Earth-like planet fills up with dust and smoke? What does that do to the climate? So there's a direct line between these studies of sort of esoteric, curiosity-driven, trying to figure out another planet, to really urgent survival skills of having a technological civilization on our planet and things we need to know so that we can have hopefully a healthy future. And similarly, you know, by studying Venus, there's a story there about how some arcane studies of trying to understand what was happening with the chemistry in the upper atmosphere of Venus led to insights that helped us figure out what was happening with the ozone layer on Earth. And there's obviously a lot of connections with climate modeling. There's some, and I won't get into the arcane details, but there's some specifics of trying to understand the radiative impact of clouds and the subtleties of carbon dioxide absorption, of infrared radiation that seem like minor distractions when you're modeling Earth, but are really important in trying to understand the climate of Venus. And then you look at that and you go, oh, well, actually, we haven't been doing this quite right on our Earth models because it didn't seem so important, but then you make sort of incremental improvements. So there are some specifics of how our Earth models have gotten better by trying to get the climate of Venus right. And similarly with acid rain, you see these sort of extreme examples of environmental problems on other planets that then help us realize things. So on that level, there's a tremendous value in convergence of having people using the same tools but working in different environments and learning things that then have practical benefits here on Earth. There's also a whole other side of it, which is the value in education and communication. And I mentioned briefly in my introduction that just having a different way of talking about an issue like climate change, saying, well, let's not even talk about Earth for a second. Let's talk about this other planet. It can sometimes kind of shake up the entrenched dynamics of the conversation. And I've seen that in action. And the last thing I'll say is that I've learned that there's a hunger in young astronomers to find ways to make their work more relevant to Earth climate. There's this group called Astrobites that is basically a bunch of young astronomers that put out regular stuff on Twitter and on the web, helping to interpret astronomy papers for people that aren't experts in whatever the Astrobites is a very good site. It's with like explanations of new science, clear explanations. But then they started doing these every year, these Earth Week summits, Astrobite Earth Week summits, which is basically the theme is training young astronomers to find ways to make their work and their expertise more relevant to helping to solve Earth climate problems. And I had a chance to be a speaker and a panelist at one of their Earth Week events. And I was just amazed at and sort of encouraged by all of these young idealistic scientists saying, yeah, we're interested in astronomy. We've got this expertise, but we also recognize that we live on a planet that's having kind of an emergency and that we know things about radiation and physics and you know, things that are relevant. What can we do to help? And so there's a real desire there among young people in the field to foster this convergence. And I think that's something that can be, you know, ought to be, we need to help them with that.
Excellent. We're going to loop back and loop in Martin now. Martin, thanks for persisting as we bring you back in. If you didn't hear the intro question, it is just, can you introduce yourself, a little bit about your work and especially what brought you to your field? Why are you where you are right now?
Okay. Well, yeah, to start with, I'm at a hotel in Mainz, Germany, and it appears to have an irregular internet connection here. So if there's a problem, I won't be offended if we move on without me here. I would say that I characterize what I've done over my professional career as exploring life with my community. And for essentially that whole period, through the lens of or a thematic view of Gaia theory, Earth as a single living system. And so mostly I'm kind of interested in it from the standpoint of us here on Earth and how we understand our part of being part of nature. But inevitably in understanding that and the ways that the Gaia theory came about, we understand our planet in relationship to others and learn from that. One example just might be, say, the preservation of our ocean, just because of the fact that, say, photosynthesis allowed excess oxygen to enter the atmosphere and tie up the hydrogen that would otherwise be lost to outer space. And who knows, maybe that's why Mars lost its water. That's just an intersection point. Mostly what I'm interested in is looking at how we understand Earth's living system and our role in it. So as far as how I got to this conference, I had a nice conversation with Timothy Spuck, and he had come to a conference that we put on in DC at George Mason University on the Gaia theory back in 2006. And I guess that's where actually he might have come to a program that I did at a center that I was working at, but we did put on this event in 2006 that has connected me with a lot of people who we still keep in touch about how we understand the world through a lens where we don't just use the idea of Earth system science in a technical sense, but keep that metaphor, Gaia, Greek goddess of Earth. I always find the intersectionality between kind of the humanities end of things, how that title came to be of not only interest, but perhaps great value. William Golding, who wrote Lord of the Flies, suggested to James Lovelock the idea of using the name Gaia, because he said it would honor the fact that our Western science was now rediscovering what our Western ancestors knew, kind of a gut mythological level. And I think that's why it's really important to keep metaphors in place to be able to have a convergence between our humanity and our humanities and our sciences and everything else that we're going to need to get us out of the mess that we're in. So I'll leave it at that. I didn't follow the first part of the conversation very much, so I'll join back in, I hope.
Well, we're on our second question about the research topics of Earth and space. And David already answered, so I'll open this up to somebody else. But the question is, what are or could be the impacts of convergence across the Earth and space sciences, especially just in your own fields? Anybody can jump in from the... Go ahead.
I'll jump in, and since I'm not from the discipline, but both these things intersect with what I do. I'll speak a little bit about a convergence accelerator phase 2 grant that I have. It's myself on the cyber infrastructure side, Laura Condon, who is a hydrologist at University of Arizona, who's the PI. Peter, who is an astronomer at Princeton, who leads our ML team, and then Reed, who also is a hydrologist at Princeton. Now, the convergence was Laura attended as a brand new faculty member on our campus a workshop that my project Cybers was doing, which is called FOSS, Foundational Open Science Skills. It's meant to teach groups how to bring in open science methods, tools, and techniques. And so she attended that and she said, I need my lab involved in this. And then the whole lab came together. And then they said, oh, these container technologies, we should be applying it to hydrology. And we said, sure, we can help you with that. And then she said, there are bigger questions we have to answer, but this reproducibility of machine learning workflow would be helpful. Peter shows up, Reed shows up, and we're like, maybe we should apply for a convergence accelerator grant because we can do cool things together. We are all from 3 different disciplines. And if we put our heads together, we can do something really meaningful. And that meaningful thing, and as you were mentioning, was Peter knew something from astronomy that the hydrologists were struggling. And if I were to sort of just simplify it at some level, there was a massive simulation that's run to do continental scale simulation that consumes millions and millions of CPU hours, takes a really long time. But then a person asking questions from a very localized, what happens in my county if the rainfall is this and this and that, how would I do more precise answering to that question without having to rerun that whole simulation for months? And so we said, yeah, we could build a machine learning scenario generator, which has learned from this bigger system, and then we can refine it with local input. And so that was our collective sort of way to come together. And I'm happy to say we got the phase 1 grant, we got the phase 2 grant, and now we have finished our work for the phase 2, and now it's being open to the community. So what this has allowed is to take what the astronomer knew really well and then repurpose it for a hydrology question. Similarly, there was an exoplanet work. So I teach a course in the same department that Gretchen was in fall. It's called Applied Concepts in Cyber Infrastructure. And we bring in a real scientist with a real computational limitation to their questions. And turned out Jared Mallis, who is a astronomer in our department at U of A, who works on exoplanet, but he uses adaptive optics. So he puts these really awesome mirrors in the telescope and then is able to detect these exoplanets or find them. Well, it takes him 3 days to capture the data and it takes 6 months to process the data. And so he was like, can I do this in 24 hours? And so that was the question for the students. And keeping in mind, if they don't solve this question, they can't graduate. So it's a pretty clear connection for the students. And more importantly, the empathy is there because they see a real scientist saying that if this can happen this quickly, I could do more. And so the students worked on Jared's project and they were able to, in 24 hours, process the data that was captured. So the next night, they already know where to point rather than come back next season and then point it there. And that was really important. The best part that I had fun was the team that did that. We had about 4 teams in the class, was led by a student from plant genetics. Okay, so none of the students had background in astronomy. They went to the IEEE conference to present, and I forget, it was somewhere in the UK. And we sent this student, so the student finished his presentation and they asked, who's your advisor? And the student gave the name and they're like, I don't know this person in astronomy at U of A. They're like, no, my faculty mentor is in plant sciences. And the audience was completely confused why a plant scientist presenting on exoplanet detection. And so I think that the moral of the story is, if you make your discipline more welcoming to others, you always benefit by that perspective. And then you start working as a team. And the example from hydrology and plant sciences, all of is connected. And to me, the convergence is meeting of the minds of 2 or 3 disciplines where you have a shared vision and you're willing to learn and grow together to do things that were otherwise hard to do.
Martin or Gretchen, would you like to tackle that one? And let me know if you want me to repeat the question.
I
Martin?
think you're muted.
As said, I'll jump in just so I can get in case I cut out later. in terms of that intersection, again, I dwell most at the level of how do we understand Earth systems, but I think about how we learn, and I use the term child mind every once in a while. It's not mine, of course. It's used in terms of looking at things with a fresh eye and not being confused by extraneous facts, et cetera. And yet that can be the starting point from that can be anything. It can be just observing the world, or it can be a scientific insight. And I remember the first scientific insight about something out of our planet was about the sun, and the fact that the sun had been heating up ever since life began on the planet 3.8 billion years ago, and that all other things being equal, we should have been fried off the surface eons ago, but that we weren't, and that in fact, over a vast geologic period, the temperature of Earth has remained remarkably constant, up and down a little bit here and there, producing ice ages and warm spells, but that's still extremely constant over vast periods of time. And that to me was the aha moment. It was the aha moment in which I was realizing that everything on the surface of our planet, rocks, water, air, human beings, organisms, everything form one system that is evolving at least in response to that, so that, or with the result that life continues. And that aha moment for me led me to really feel like the Gaia idea, where you both have Earth as a single system, but us as a absolutely seamless continuum of it, is the body of knowledge, the lens through which we have to understand our world. Otherwise, everything is completely siloed and separated. So at least connecting with what the sun is doing over vast time, we can understand a huge relationship with our lives here on the planet. I'll leave it at that.
Okay, there's something I wanted to say that I forgot to say, and I'm gonna just say it really quick before getting into the topic, but I just wanted to thank the folks at AUI for making this virtual component of the presentation possible. I really, really wanted to be there in DC and was planning to travel, but wasn't able to because something came up. So thanks to, Tiffany, Amanda, Tim for making this possible. So, okay, thinking about possibilities for convergence, not being myself an earth scientist or a space scientist, I can only speak from the information management perspective. So, one of the important parts of conversations about convergence is it always ends up being about data. Where do we get the data that we need to research these complex problems, and how do we deal with the complications of sharing information and data across disciplines that may have different standards, norms for conducting research, different types of instruments. How do we integrate all of that information successfully to better understand the universe? So, in thinking about what might be possible with Earth and space science convergence, I think we need to think about what we aren't thinking about yet, like the unexpected discoveries that can come out of working out these systems to do better convergence. So as we think in terms of complex problems, we need data over longer timescales, and innovations are happening, as we're thinking along these lines. Innovations are happening in the way we share and organize information and data and the way we collaborate, including, as we all know, we're in a frontier of artificial intelligence and simulating very complex processes. But I'm going to take a little step back because my research has focused on questions around the value of older data for society. I'm thinking about smaller or more dispersed data sets that currently might be of interest to only a few people or to specialized research communities. Now, Nirav mentioned how Cyverse democratized computing for lower resourced institutions and ensuring that these communities have access to cutting edge technology. And we kind of see the same dynamics with data. There are certain research areas that aren't well supported for good data management. But if we can gather up all of these, smaller researcher held data and integrate what tends to be more boutique data sets with larger data sets and archives, we might make new discoveries that we haven't even thought about yet. So this is thinking about the data-centered processes through which we can enable transdisciplinary convergence across domains. It's not necessarily easy or straightforward, but one cross-cutting topic is open science. And we know that making things like data and software available in a transparent way can have positive benefits on researchers and research processes. And, we have increasing incentives to do open science, like funding agencies require data management plans. We have all of these acronyms and principles for encouraging people to make data. For example, the FAIR principle is findable, accessible, reusable, interoperable. But, open science is ultimately a social engineering problem. So, we're creating all of these technologies to interconnect information and make it easier to be transparent with how we're doing research. But the question is how and whether people can comply with these initiatives, especially coming from very different areas of expertise. So I think that that's one of the key challenges to convergence, but as I said, also an opportunity as we're smoothing out these processes to make it easier to have new discoveries later. Something else that we might talk about later in a later question is making scientific information widely available can also lead to misinterpretation of specialized knowledge. So we've been seeing dynamics like that throughout the pandemic, and this is a big issue for science communication. So some of these dynamics also play into convergence where, if experts in different fields come together and try to share their knowledge with each other, that's a struggle. And then what about the part, communicating what's going on there to the public? So I worry a little bit that convergence might be more vulnerable to misinterpretation, but that's maybe a point for another topic. So yeah, I'm interested in what we should focus on saving. And there are researchers who, in my field, who believe that this is the question of our day. Is the data that a scientist collected a decade or 2 decades ago stored on a tape that can no longer be read without specialized equipment that you have to buy off of eBay, is that worth saving? And I think many people would argue that yes, because we don't always know what will be useful in the future. But we can also support discovery and research that depends on long time scales to make more robust models of reality, such as, climate modeling and transient phenomena in the sky that astronomers may study, for example. So again, I think we have a lot of challenges, but there are also a lot of opportunities in the way we're improving these systems of sharing information, communicating, and organizing our data.
Thanks, Gretchen. I do have multiple more questions, but I thought I would pause for a moment and see if anybody in the group or if anybody online has questions for the panelists, or just something that's coming to mind that you're wondering.
I don't need the mic, do I?
The whole room is mic'd.
Okay, all right, good. So this is one along the lines of something Gretchen said here. So there are those individuals who are pack rats, and those individuals who, do cleaning every week and throw out the stuff that is not necessary. But if you've walked into someone's home who is a real pack rat, a real artist at it, you can barely navigate through the home. And so I think we're getting to this question about organizing data in a way that is useful across disciplines without, sort of being the pack rat, but being the organized pack. And, as new things as we come up with new data, we come up with new ways of understanding data. How do we ensure, like, if we want this historical data, there needs to be systems in place that are going to, or whether it's AI or some way to automate so that that historical data can be tagged in a way that it doesn't confine or constrain new data, new ways of looking at things. But at the same time, if you want the ability to do longitudinal research, you need to ensure that that old data is tagged in a way that it can function with new technologies. And how do you deal with that?
I can say a few things. First is for the pack rat, which is an important person in every discipline. You have to figure out how to make that pack rat be a good storyteller. Because if you cannot associate value to that data that is going to be of interest to the funding agency or to some person with cash, I don't care who you are, the day that pack rat retires or dies, whatever comes first, it's a game over. Now, you may have a collection of pack rats, but typically they all like to live together, but they all have the same lifespan, right? So we really have to be cognizant of generations of scientists that come and go. And we lose a lot, not just the data, but what that indexing of that data is in that pack rat's head. And they know what is where. So even if you digitize that and you come up with whatever standards, if there is no digital twin to that pack rat, you're screwed. And so I think it's really important to think of that in terms of, and I'm just using the word pack rat, but you get where I'm going with this. If you want to make sure that that is usable, I don't think we have to obsess over the tagging or the extraction of the data, where you start seeing the technology evolve. For example, again, I'm not trying to sell a technology, but you look at one-shot learning. Now, you can have something where you've taught it once and it can extrapolate safely and do other things and detect what you need to. But that one shot, you needed the understanding of that pack rat to at least do it once. And if that pack rat is not there, it's hard. And I've seen that happen in life sciences more frequently, where my colleagues could look at an electron microscope and say, that's that boundary of that brain, that's this, that's this. Once that person retired, literally none of her students, who are now full professors, have that same skill because they didn't spend hours doing what she did. And now all her life's work, which is still like one of its kind, it's there, it's digitized, but there aren't enough people to work with it. So I don't expect it to be different in astronomy or other disciplines. So it's important to find a digital twin of the pack rat before they retire.
I have a very quick anecdote that illustrates recently from my field that illustrates the problem you're describing. So in planetary exploration, as I mentioned, the first missions were in the 1960s and 1970s, and they were typically smaller teams of researchers. It was a new field, and a lot of the data did not get well archived or well preserved. And there's a lot of sad stories, and you've probably heard some of them of some of the original Apollo data being lost because things weren't digitized properly and the film fell apart or whatever. But right now in my field, we're excited because we have several new missions to Venus approved for to launch the end of this decade, which is something that I'm pretty involved in. And the last time the US had an entry probe into the atmosphere of Venus was 1979, a mission called Pioneer Venus. And there's new attention to those results now because we have a new entry probe that we're going to launch in 2029, and we're going to get the data back in 2031. Now, of course, a lot of the researchers from that mission in 1979 aren't around anymore. And unfortunately, a lot of the data isn't around anymore either. And in particular, the papers that they published, we have, but that was sort of interpreting the data according to the tools they had then. And recently, it's come out that there was a guy at NASA Ames Research Center named Al Seif, kind of famous in my field for really being seminal in designing the entry probe and the instruments and a lot of what we learned from our first time descending through the atmosphere of Venus with instruments about the composition of that atmosphere and the radiation and the temperature and all that. Well, we have his papers, but a lot of the data from that entry probe has been lost. And now people are going, well, did they really analyze it in the right way? Well, it turns out when Al Seif, who's now deceased, when his office was being cleaned out, there were piles of paper and stuff outside the office. And some astute colleagues saw a printout that was literally one of these paper printouts with like the holes, the sprockets on the sides. And that was the only place this data existed. And somebody saw that and thought, this looks interesting. Maybe this will be useful, and kind of took it and put it in their office. And then one of my colleagues just a few months ago discovered this. And it turns out it's the only existing record of the actual data from this entry probe. And he's now publishing reanalyses of this and writing papers, which seem significant. And it's only by the luck of somebody finding this thing out in the hallway and saying, this might be interesting. So it just goes to show that combination of having a small number of people who had a lot of the knowledge in their heads, who are now either gone or mostly gone, and the fact that there wasn't any kind of systematic archiving, it's sort of the worst case scenario of what you're describing. And hopefully we're learning from that and we'll do better. And even things that don't seem like you necessarily need to archive them because, well, we analyzed it, here's the analysis. That can turn out to be like a really, really bad mistake.
Just want to make sure that Gretchen and Martin have an opportunity to address Tim's question as well.
Martin, go ahead.
Okay. I'll say that this conversation reminds me of a book by Bill McKibben. Many probably know him as the person who's currently very outspoken on what we need to do about climate change. He had a book back in early 1990s called The Age of Missing Information. And his premise was that we're entering an information age, but he took issue with that. He said, we're entering an age in which the information we need is being covered and diluted and lost in the onslaught of all sorts of other information. And he compared at the time 24 hours of cable TV in Fairfax County, Virginia, which had the most cable channels of anywhere on earth at the time, with 24 hours on a backpack trip in Vermont. And he outlined the information that he learned in each that he thought was most important to our well-being and long-term survival, and came to the conclusion that the backpack
Maybe if he turns off his video, we'll get some bandwidth.
Yeah, we did. I'll do that.
Fortunately, I think he had made the point. Ended up being informationally more valuable than the 24-hour news cycle.
Maybe I'll just jump in really quick with just a couple of thoughts. Number one, I mean, the scale of the information that we're dealing with is much bigger, more complex, more expansive. but there's some, like, in a sense, nothing's really new. You know, we always lost information and we're still, you know, doing okay for the most part. And so I think I just wanted to, you know, kind of point out that principles of traditional librarianship apply very well in this context, just like the story that David was telling. You know, it always comes down to a moment in time when someone recognizes value in something and is able to do something about it. And, you know, and we have a lot of knowledge about these principles in library and information science, such as appraisal. And so I think there's a debate about the extent to which libraries are or can actually make a difference in this situation of better data management. But the principles of librarianship still translate very well to these problems.
There's another question here. I do see that there's one question from online. Can we jump there first? Just trying to keep it.
Sure. So Dan Fuka asks, related to Gretchen's topic, do we need to decrease or remove the amount of time scientists get proprietary access to their data collected with federal funding? I.e. 90% of scientists who publish refuse to share the data from their publications, suggesting that most data is hidden from the scientific community by the funded scientific community. Which suggests the only solution is requiring instant access to those funded. NREO allows 12 months of proprietary. 12 months is not considered small. Yeah. That's it. Okay.
Letting anybody jump in. It looks like
I think I want to finish the prior thread, but I think you have a question.
So,
related here.
yeah, so I think I'm kind of,
Okay.
Oh, it's,
Yeah, if it's
a follow-up.
let's follow up with that and then we'll jump into Dan's question.
Great.
so, because I think, yeah, related to I don't know, it's like the meta pack where it's, but it's in addition to the data, like in visualization, we often talk about the reproducibility of the visualization process so that you have a flow, a workflow that you're also preserving, which of course is much like the tape drives and and punch cards, is dependent on the software you're using, and the software is getting updated every, you know. So I guess the question is, are there good solutions for how we can preserve those workflows as well as the data themselves?
I can take a stab at that, but I just want to say one quick thing to the point that was made earlier. One of my colleagues on campus, she came from, forget which university in Canada, but there was a death in the department and the faculty member was gone, and the university was ready to clean out the office. And when people found out that there was a lot of data that was not digitized, faculty member had been there for a while, but they're like, it's too expensive, we don't care, and then the students and so the faculty members got together and said, why don't we do a data rescue? So they all got together, they sifted through some of these things, put it together, and they published a beautiful paper on what does it cost to do a data rescue. And that, including labor, it cost them $10,000 for that. And I'm happy to share that paper with anybody. So if you think at the university, if you have somebody who's with you for 30, 40 years, $10,000, can we just put that as insurance money and keep it for every person that you have that's producing data in your department, such that what they have done, the value is preserved and is organized. So sometimes I think we overestimate the cost of doing some of these exercises. And I think it's worthwhile for us to think that as a human being, whatever digital exhaust we are producing, can that be organized and put in a way that more science can be enabled? And I think it's very doable. So anyway, finishing that thought, I do want to answer that question, but again, I want to make sure others can.
It seems like it's related to what we were just saying.
So reproducibility and replicability, you know, people will go around and around, but at least for the discipline that I come from, what we've started seeing is the data source is referred to as a URI, and you point to it for its acquisition. And then the computational part is either well documented through a well-known workflow language and using constructs that are either having the program containerized or containerized in a sense that not a black box, but the recipe that starts from the operating system all the way to all the libraries and then the actual binaries and programs is a recipe. So when you now start looking at it, you are able to do things with it. And what I really enjoyed in the broader life sciences is that there are now repositories for workflows. And then when you go to your paper and say, I want to reproduce this, it's doable. And in my own projects, what we're now doing is also encouraging people to put a button next to their data source, because the data by itself is not very meaningful for many external groups. If it's the computation that uses that data and there is a way to put that together, it becomes even so that reproducibility coming from push this button, put some credentials here, and you can now run that workflow where you don't have to know about the underlying plumbing. That infrastructure as code will orchestrate it for you. You focus on the science rather than orchestrating the work. So anyway, so those things are happening, and I'm hoping that they become more broadly usable. But the underlying technology exists, it's just the will of the people.
Just a quick anecdote about preserving workflow. So the New Horizons mission launched from Florida in January 2006 and was, if all went well, which now we know it did against all odds in some cases, it was going to reach Pluto in 2015, 9 years later. And there was a lot of concern, what if there are things that people know on the team now, and those people are no longer in the team when we get to Pluto in 9 years. And furthermore, the technology is going to change and some of the ground systems and so forth. How do we deal with preserving all that? Because, you know, you could try to write everything down, but maybe there's something in my head that I'm actually the only person that knows. So one thing they did was they had every member of the team make a video for their future self in 9 years, or their counterpart if they were either no longer alive or no longer on the team, saying, here's what I do, here's everything I know, here's how I do it. And so that was one attempt at preserving that kind of corporate knowledge that was in people's heads.
Gretchen or Martin, do you want to address the question that was in the room?
Unfortunately, as you know, I got cut off and I did not hear the question.
Sure, so the question was around preserving not just the data, but the workflow that is used to interpret the data. And I was pulling an example from visualization where I work of creating reproducibility and results from the same or similar data sets.
Gretchen, why don't you go ahead?
I don't have anything specific to say about, you know, the technicalities of preserving workflows, except that this idea of temporality that we keep coming back to is really, really fascinating. I mean, this idea of making videos for our future selves, this is really how we need to be thinking in terms of managing the information that we're generating and working with and getting a handle on the complexities of research processes over time. I read a paper recently that, you know, archivists, for example, they're not even really capable of thinking beyond their own lifespan. So how can we think in much bigger terms about the temporal elements of research processes and develop more creative solutions to capture the information that we're going to need someday to, you know, reproduce analyses and such.
I'll jump in and just say, both between the cutoff of my internet and the way that conversation is going, I hadn't really expected it to go in this direction, and I'm kind of sitting a little on the sideline and wondering about, but it is interesting. And I think back to what my own focus is this place on this planet and these people here. And the phrase, of everything of the fathers, the goodness of the, although all sorts of things come and go, the basics of life are the same, at least, in our human, even millennial experience. And so that's why I feel like, I wonder if there's some way to take the out of this world and, in a sense, different temporal scale understandings and viewpoints and research of outer space, and keep it grounded, I guess, literally, by comparing it to that which will carry through the generations. The basic with that, but I keep going back to, we need to understand this place, this planet, these people.
I did. Martin, would you like to try turning off your video to see if that will help your connection? Okay.
One quick thing while Martin is frozen here.
Living,
So the data stories that we're talking about, isn't it? And I find it interesting that it almost parallels the stories of, for example, Indigenous persons. They're very often seen as, or sometimes called, mythology or things like that. But that's stories that they handed down from generation to generation, which was the preservation of the processes or preservation of the story and the understanding of their observations of their data that they were collecting. And in a sense, we're talking about, in modern science, or this idea of preserving the story of the data, because the data itself loses meaning if we don't have the story. And so, to me, those things kind of feel like they parallel each other.
Go ahead. We're having a good conversation, yeah, and we'll see if Martin can get back in and wrap up what he was saying. And we also have, Dan has a question online. Ken has a question here.
Okay, so I don't know if we'll have time for all of our questions, but we, at least two of our speakers will be here for a little while. We have plenty of time for casual conversation for lunch, so.
Given that both of us will be here, why don't we allow colleagues online to?
Excellent. Martin, now that we have your video off, we might be able to hear what you were saying. You were glitching out quite a lot in the last piece. So if you can summarize what you were saying. If you can, assuming you can hear what we're saying. Okay. I'd like to get our Dan's question back onto the table, and then Ken's, and then I might have one more on our list.
I can reiterate. So Dan was asking about the need to decrease or remove the amount of time that scientists get proprietary access to their data collected with federal funding. Give a comment on that.
I can speak to life sciences. NIH just this January changed a lot of those where they said this has to come out much sooner. And interestingly enough, they have put in clause where your continuing funding depends on you meeting that. So it's really interesting to see that earlier, none of these policies had teeth. And now the change in the NIH data management policy actually has up to the program director to intervene and say, the next round of funding is not coming in till you meet what you said you were going to do for this last year. So it's just, I think I'm not from this discipline, so I don't understand the nuances of the publication life cycle. But I think everywhere we're starting to see, if you are paid to generate data and others are relying on it, you no longer can say, I didn't have time to do this. You have to plan it out and have your analysis team ready. But you cannot keep using that as an excuse. Or, I mean, I don't mean it negatively, just.
Yeah, I just going from perspective and experience in my field, I think there is a good rationale for a proprietary period for certain kinds of data, but there's no reason why it has to be very long. You know, if people put a decade or two into getting an instrument to another planet, and then you know, the day after that flyby, somebody else comes out and publishes a paper because the data is completely open, and you know, that's not quite right. They sort of deserve a chance to have first crack at it, and they probably have better insight in all kinds of ways into you know, the limitations and context of the data. But you know, in my view, that could be 90 days or something like that, and then you know, let them have first crack at it, and then let the world have it.
Gretchen?
Yeah, I mean, I think this question really varies across fields, but in general, the sciences are still not fully set up to culturally to accommodate the new mandates that are uncomfortable for a lot of people to make data available, because there's so much competition, especially like myself speaking as an early career researcher. There's tremendous pressure to publish new and interesting findings, and you absolutely don't want someone else using your data before you're done with it, because they are probably working on something close to what you're working on. And this is really a question for convergence too, bringing it back to convergence. Like, what are we really incentivized to do within this academic system? What are the unique pressures that we're all under in these different areas that we're working in? And I don't think we're really yet fully incentivized to step outside of our disciplines very far. And we're not sufficiently rewarded for it, especially as an early career person. The important thing for us is to publish in the right journals, get noticed by the right people, spend our research money and time going to the right conferences. And so these tension points, or this discomfort, kind of reflects that science hasn't fully adapted to the ideals that we want to work with. So yeah.
Thank you. Ken, you had a question.
I did. What role do you see citizen science and perhaps even artificial intelligence playing in this acquisition and cataloging of data and synergizing?
Again, I'll give an example which is not exactly from this discipline, but something that we recently did, and it's only possible because of citizen science. There's something called iNaturalist. How many of you have heard of it? Right? Yeah, right. And so I have one of I'm part of the National AI Institute for Resilient Agriculture, IRA, and we had to focus on creating a machine learning method for the robot to, when it finds an insect, to understand what that insect did, and is that insect agriculturally important, and should it be sprayed or not sprayed? What's the strategy? So the easiest thing to do, and I was surprised how many people did not know of this, that iNaturalist actually has the licensing now aligned, and they will also have a way for you to see if this is research grade. What that means is that two different people have agreed upon, which I know sometimes is hard, that this is the right taxonomy, this is this insect, and the metadata for the location and everything else is there. So it is called research grade. And Amazon Web Services had given them a place to keep all of this. And so within like a few days, some of my students wrote the program to bring in terabytes of data. The groups that were building the models, some at NYU, some at Iowa State, were able to pull all of that data, create a method that is surprisingly so accurate that we were like, is this really that accurate? Like, we didn't believe it, and it is. And so now it's quantized, it's put for the robot to work at edge computing, and now it's becoming a paper. All of this happened in 6 months. Now, if iNaturalist didn't exist, this wouldn't even start, because for us to collect that level of data in multiple fields, in multiple areas. Now, keep in mind, everybody loves to take photos of ladybugs, and nobody takes photos of cockroaches or whatever. It's just human nature. So you have some things overrepresented and some not. But training on that, there are statistical methods that will allow you to compensate for class imbalance. But citizen science, to me, is at the center of a lot of things that we could do, and we could do even better. So I think every discipline has to figure out where to bring in the citizen science, but more importantly, not give them busy work, but take what they enjoy. And so my own campus, there's something called the Natural Phenology Network, where they capture data, again, thousands of people, and they give you meaningful data. It's up to you how you want to leverage it. So I'm sure there's opportunities galore, but we want to make sure that the platform is there where that data becomes available and they are acknowledged for their contributions, because this is a lot of work.
Anyone else on the panel want to?
Well, just really briefly, in certainly in space science, citizen science is huge. I mean, and the potential for it is huge. You've got amateur astronomy is becoming more and more affordable to many, and the kind of equipment that can be deployed by hobbyists now dwarfs what professionals had not too long ago. And so in that, and also various kinds of data analysis tasks where people, if they're interested, can like sign on to some project and help. There's a lot of kinds of data analysis of say planetary surface data sets and so forth that eyeballs still do a much better job than any kind of machine analysis. And so the potential there is huge, but it does create problems of, how do you deal with quality control and reduce all that data with all the different kinds of biases and everything. But what you just described, I think it is a large part of the answer. And it is a way that like sort of AI properly deployed can really help sort of rein in all that potential of citizen science and turn it into something that is really creating useful data sets. And so I think it's you asked about two different things, the citizen science and the AI, but it sounds like potentially the combination of those two is a really powerful aid to science. Yeah.
Gretchen, any thoughts?
Yeah, I suppose we can't conclude this event without mentioning ChatGPT. In thinking about the role of AI in classifying and understanding information, there's a discussion going around on a listserv that I belong to in library and information science about using ChatGPT to analyze qualitative research data. As social scientists analyzing qualitative data, we typically work with interview transcripts or documents and painstakingly use our brains to understand the themes that are emerging from the textual data that we're working with. But now people are able to feed it to ChatGPT and it will instantly tell you what the main themes are. So I think that we have a lot of questions right now about the role, the agency of the researcher, that we need to deal with in thinking about how we use AI to understand and classify our data.
I do want to add one thing, which I want to add one thing which I've sort of seen more from the NIH side, which is return of results. And so when you have contributed your data and you have to get something back, what is it that you're giving that person back so that they feel valued in that whole ecosystem is really important. So we typically, as scientists, design it for our own interests, and then we treat the busy work offshore to either the citizen scientists, and we say, thank you for your data and give you a badge or something. But there's a lot more to it. And I think this morning, for some reason, I decided to read up on the shoemaker Levy, and given they were from Flagstaff, she was essentially a citizen scientist and did amazing work. And of course, I don't know why, but this morning I decided to go read up on that. And so that I think is important for every discipline, the return of results and acknowledging and making sure that they're not doing busy work.
Excellent. I have one final question for our panelists. We have a lot of educators in the room. What opportunities and challenges for data literacy and STEM education are afforded by Earth-space convergence? Opportunities and challenges.
Or
Education, either STEM education or data science literacy. You know, we've been talking about things that kind of are all in our worlds, but we need to get out into the public, and the way we do that might be through education and literacy.
Well, I mean, one of the big challenges is sort of siloing of expertise and the languages that we have in our separate fields to describe things, and the fact that you know, that we all have our own jargon and our own ways of thinking, and so we don't always converge in that sense. But you know, so the opportunity, of course, of thinking this way is to help us break out of those silos. And often we find that when we do so, that's where a lot of the really interesting results and a lot of the really interesting science is, because things that have fallen between the cracks, and those silos are reinforced by so many things, you know, not just our academic training and ways of thinking, but the funding programs tend to, you know, you're working on either this or that, where the thing that's kind of both is there's nothing to support that. But I find that there's a synergism between, you know, this is where the educators can help us and vice versa, because when you if you're successfully communicating, then you're abandoning that jargon. And when you sort of in more just straightforward common sense language, I mean, you know, who was it, Feynman or somebody said that if you can't describe something in plain language, then you actually don't understand it yourself, you know? So I think the convergence and communicating in a way that is successfully enacting that convergence can actually help us find those interesting points of science that are sometimes lost in the cracks. And in that way, there's a synergism between working with communicators successfully and feeding back on helping the scientists to break out of their own silos. So.
See if Gretchen has a thought.
Seems like Nirav wants to say something. Go for it.
Gretchen, you go ahead. You have the right of way.
I guess I was just going to say that something similar to what David said. In all of my activities with NEREID, I've been hanging out with this group for some years now, and interacting with a lot of STEM educators. I've observed that educators are on the ground and observing these opportunities for crossing disciplines and topic areas in a way that we, you know, siloed researchers may overlook. And they're hungry for convergence, opportunities to access new technologies, access researchers and research spaces for innovative ways of inspiring and teaching students. So I think that feedback loop is really important, how we continue to facilitate a feedback loop between research and education and vice versa to continue to bridge these topics. On the topic of science literacy, that's a whole other can of worms that I don't think we really have time to talk about in the next few minutes, but getting the public in general to understand the flaws of science, how science is done, how imperfect it is one of the biggest challenges that we're facing. I'm just, we have a couple minutes, so I'll stop there.
So I can speak to this with few different hats. The first I'll wear my hat as the director for the Data Science Institute, where we often get asked, can you come give a lecture on AI or use of AI or large language models? And that is a good way to engage, but in reality, if you want to engage with the educators and do something sustainable and substantial, we've learned that we have to walk in with enough components that are not going to add burden to them to integrate what we are trying to do into their learning workflow, whatever that might be, but then give them the guarantees that, hey, if you're using our infrastructure to teach this course or this workshop or whatever that may be, for the next 3 years or 5 years, this is going to be there semester after semester, and you're not going to have to rewrite your lesson plans or whatever that might be, but then build a community. So I've been so fortunate that many of the institutions started a program, took what we had, and then they formed their own informal community that spans the whole of US. And then they trade and exchange material that has allowed them to rely on what we provide. And our guarantee is that your class next year will be able to use exactly the same thing, and there will not be surprises, but you have to redo your materials. That's lesson number one. Lesson number two is that it has to have some interesting hooks. If you teach data science literacy without that excitement of what is contextual and more recent, it is difficult to engage the community, the students. And it often, the educators don't have the chance to do all of that. So we try and find ways to take something exciting, bring it in and integrate that into the lesson plan as a bonus or whatever that might be. And the last thing I'll say is with the large language models and Chat GPT and other things coming in, and I think Gretchen hinted to that, the ability to ask it to behave like something else, which broadly falls under prompt engineering, where you say, now behave like a person that only knows this much or this has a background in this mathematical context. And now tell me how I would explain this paragraph to them, and having it rewrite that paragraph. And so de-jargonizing something becomes much easier with some of these methods. So I'm really excited about how we can bring that into making the barrier to entry much lower, so that these things can be still important and framed in the right way for the community.
Well, we have come to the end of our time. I'd like to thank all of our panelists and the room for your questions and involvement.
Yes, thank you, Gretchen. And I'll thank Martin for on behalf of all of us as well. I know it's frustrating. I've been in that position before, but I appreciate you for sharing your expertise. It's a wonderful conversation. And now it's food for thought while we go eat the literal food that's back there. So lunch is ready. You guys would like to make your way back where breakfast and refreshments were served in the orange room. We will over there. We have about an hour, and then we will be back for our lightning talks.
Bye, everyone. Thank you.
Hi, Gretchen.
Thanks.
It's good to meet you again. Hey, oh yeah. I'm Brett. Yeah. I won't come. But I'm not.